recording.
More theater sermons. So we're getting connected here. It's a lot of fun. So thanks again, Margaret. And I will pick up your recording because I have to head out right now. But thank you all for being here. And Jeff's here in person, so he's going to convey any questions he has through Brenda. And thank you, Brenda, for all of this. And Janetta for recording it. Oh, what a team. Yay, team. See you later.
Thank you, Hallie.
Thanks a bunch.
The U-Bar-U Ranch is going to have a specifically star-related weekend in late August.
Good.
That is, if you go to that website and look for it, you know, that if there are people that are interested, I think it's the last full weekend of August.
Okay. Well, most of y'all know me, but my name is Margaret Davis, and I'm a long-time science fiction / space fan. When I heard that this year's Northwoods Service Auction theme was going to be Northwoods is Out of This World, I was so excited that I decided to put together 2 presentations in support of this theme. Today's presentation, The Night Sky, is about our solar system, the planets, and the unmanned NASA probes and rovers. The second program, which will be in September, is called Space Flight, and that one is about the manned space program, both NASA and other countries, and now private commercial astronauts, and even the space tourists. Thanks, and let's get started. My presentation is primarily short videos with some slides in between, and Brenda Cooper is helping me. There we go. Okay, so like I said, it's mostly the videos. We're going to begin with the grand tour, and this is the mission of Voyager 1 and Voyager 2. Then we're going to do the Mariner mission, which was 1973, and the Mariner went to Venus and Mercury. And then we're going to talk about Curiosity and Perseverance and how they landed on Mars, which is quite amazing. Then we're going to do Jupiter, and yes, Jupiter hit by a comet, and we're going to talk about Pluto. And at the end, we're going to be going over Hubble and the Webb Space Telescopes. Okay. The concept, the idea of the Grand Tour started in 1964. Gary Flandreau of the Jet Propulsion Laboratory came up with the idea. He noted there'll be an alignment of Jupiter, Saturn, Uranus, and Neptune, such that it would occur in the late 1970s. It would enable a single spacecraft to visit all the outer planets. And to do this, the spacecraft would use gravity assist. This particular alignment occurs only once every 175 or 176 years. So I really am thankful to Mr. Flandreau for figuring this out in time so that Voyager 1 and Voyager 2 can be put together and launched. Okay, you need gravity assist if you cannot take enough fuel with you for your entire journey. And you need the gravity assist to speed up to get there faster, to cut some time off, how long it takes. So what you do is you steal some momentum by getting very close to a planet. Okay, so we're going to see a short video here.
first of all, getting anything off the surface of the Earth is really hard.
Okay, we
But
need
reaching some
to see the video,
faraway destinations in the solar system is even harder.
but we can't see it. Technology is wonderful. There we go. That's great music.
Hi, I'm Tim, and I like science. Did you know that a spacecraft can use a planet's gravity to change its orbit? It does this by using something called a gravity assist. But what exactly is it, and why would we ever need to use one? Well, first of all, getting anything off the surface of the Earth is really hard. But reaching some faraway destinations in the solar system is even harder. This is where gravity assists come in. Conceptually, it's really pretty simple. As a spacecraft gets closer and closer to a planet, it starts to be affected by the planet's gravitational pull. The closer it gets, the stronger the pull. But don't forget though, the planet isn't just sitting still, it's moving through space, and so it's carrying momentum along with it. Essentially, as the spacecraft moves through the planet's gravity field, it steals some of this momentum, curving its path and changing its orbit. For example, when the OSIRIS-REx spacecraft launched in September 2016, the rocket wasn't powerful enough to send it straight to asteroid Bennu, its target destination, so we needed to find a way to use nature to help get it there. In this case, it had to go all the way around the Sun and come back to the Earth a year later. We're then using the Earth's gravity to change its orbit and help put it on course to Bennu. With the help of this gravity assist, OSIRIS-REx is due to arrive at the asteroid in August of 2018. In the meantime, keep following the adventure on the web and get set for what's sure to be an incredible.
Okay. Can we bring the slides back up? Okay. Okay, I love this picture. Okay, so Voyager went to Saturn, Jupiter, Neptune, and Uranus. Okay, other missions went to Venus, and Pallas is an asteroid, and Ceres is a dwarf planet, and of course there's the moon. So we're not talking about everything, but just to show them all on a line. I just think this is such a cool picture. Next slide. Okay, so Voyager 1 did Jupiter and did Saturn, and it particularly was going to visit Titan. Titan is larger than Earth's moon, larger than the planet Mercury. It's the only moon in our solar system that has clouds and a dense atmosphere, and the only world apart from Earth with liquids on its surface. So Voyager 1's assignment was to get a close-up of Titan. This left Voyager 2 to go visit all four of the gas giants. Next slide. Fun planet facts. How many planets have rings? Well, when I was growing up, it was just Saturn. Answer. It turns out Voyager showed us all of the gas giants have rings. Saturn, Jupiter, Uranus, and Neptune. So we first saw Jupiter's ring because of Voyager. We go, oh, look at that. Saturn, of course, we all knew has wonderful rings. Okay, we found out Uranus does all this on its side. It's tipped over 90 degrees. So that's a unique thing for Uranus. And there's Neptune, and it has more rings than Jupiter or Uranus. Okay, next slide. Okay, now we're going to do one of my favorite videos. This is really terrific. We're going to start this one. I love the music. Okay, so this shows, it's an animation, shows the motion of the planets, and it shows our probe, Voyagers. And you'll notice that Voyager 1 went to Jupiter and Saturn, and because it went to Titan, then it just left. Voyager 2 went to all four of the galaxies. Voyager going up to the upper left. This is showing us where the planets are. Voyager 2 actually launched. Voyager launched, or Voyager 1. I showed you the gravity assist because I'm not enough of a physicist to really make me of that chart. People who know physics don't understand. Okay, so here comes, this is the good part. Here comes Voyager from the lower right, coming right along. Voyager got real close to Io. First shows that the Io flyby. Okay. Voyager 1 didn't get close to Europa. It's going straight down. Now Voyager 1 is dead. Callisto looks a lot like our moon.
Josh!
Like Mercury. And Voyager 1. Now Voyager 2. Here it comes. Voyager 2 is Callisto. Voyager 2 never got close to Io. And Voyager 2 got close to Europa. Got a flyby of all four Cali. Gravity assist Voyagers. Here comes Voyager 1, and this is the all-important Titan. Bye-bye. Bye-bye. Honestly. Here comes Voyager 2. Got a big puzzle. Here we see some gravity. Boy, is that changing the Voyager 2. It's the Uranus, and astronomers do call it Uranus. And again, some gravity assist. Okay, we're going to bring the slides back. There we go. Yeah. Okay, now this is my second favorite of all the videos. Landing Curiosity on Mars, otherwise known as the 7 minutes of terror. Okay, we want to start the video.
When people look at it, it looks crazy. That's a very natural thing. Sometimes when we look at it, it looks crazy. It is the result of reasoned engineering thought, but it still looks crazy. From the top of the atmosphere down to the surface, it takes us 7 minutes. It takes 14 minutes or so for the signal from the spacecraft to make it to Earth. That's how far Mars is away from us. So when we first get word that we've touched the top of the atmosphere, the vehicle has been alive or dead on the surface for at least 7 minutes.
Entry, descent, and landing, also known as EDL, is referred to as the 7 minutes of terror because we've got literally 7 minutes to get from the top of the atmosphere to the surface of Mars, going from 13,000 miles an hour to 0 in perfect sequence, perfect choreography, perfect timing, and the computer has to do it all by itself with no help from the ground. If any one thing doesn't work just right, it's game over.
We slam into the atmosphere and develop so much aerodynamic drag. Our heat shield, it heats up and it glows like the surface of the sun. 1,600 degrees.
During entry, the vehicle is not only slowing down violently through the atmosphere, but also we are guiding it like an airplane to be able to land in a very narrow, constrained space. This is one of the biggest challenges that we're facing and one that we had never attempted on Mars.
Mars is actually really hard to slow down because it has just enough atmosphere that you have to deal with it. Otherwise, it will destroy your spacecraft. On the other hand, it doesn't have enough atmosphere to finish the job. We're still going about 1,000 miles an hour. So at that point, we use a parachute.
The parachute is the largest and strongest supersonic parachute that we've ever built to date. It has to be able to withstand 65,000 pounds of force, even though the parachute itself only weighs about 100 pounds.
When it opens up that fast, it's a neck-snapping 9 Gs.
At that point, we have to get that heat shield off. It's like a big lens cap blocking our view of the ground to the radar. The radar has to take just the right altitude and velocity measurements at just the right time, or the rest of the landing sequence won't work.
This big, huge parachute that we've got, it'll only slow us down to about 200 miles an hour. And that's not slow enough to land. So we have no choice, but we've got to cut it off and then come down in rockets. Once we turn those rocket motors on, if we don't do something, we're just going to smack right back into the parachute. So the first thing we do is make this really radical divert maneuver. We fly off to the side.
Diverting away from the parachute, killing our horizontal velocity and our vertical velocity, getting the rover moving straight up and down so it can look at the surface with its radar and see where we're going to land. And we head straight down to the bottom of a crater, right beside a 6-kilometer high mountain.
We can't get those rocket engines too close to the ground, because if we were to descend propulsively with our engines all the way to the ground, we would essentially create this massive dust cloud. That dust cloud could then go and land on the rover. It could damage mechanisms and it could damage instruments. So the way we solve that problem is by using the sky crane maneuver.
20 meters above the surface, we have to lower the rover below us on a tether that's 21 feet long, and then gently deposit it on its wheels on the surface.
As the rover touches down and is now on the ground, the descent stage is in a collision course with the rover. We must cut the bridle immediately and fly the descent stage to a safe distance from the rover.
Air mighty things. That was their motto. Okay, so now I'm going to show you Perseverance, and it went through the same maneuver, but it had cameras on board, so we could see video while it was landing. So go ahead and start the Perseverance. Yeah. Yeah.
We are starting the straighten up and fly right maneuver, where the spacecraft will jettison the entry balance masses in preparation for parachute deploy and to roll over to give the radar a better look at the ground.
Indicate chute deploy.
The navigation has confirmed that the parachute has deployed, and we are seeing significant deceleration in the velocity. Our current velocity is 440 meters per second at an altitude of about 12 kilometers from the surface of Mars.
And you can watch on the bottom. It'll show.
Perseverance is now slowed to subsonic speeds, and the heat shield has been separated. This allows both the radar and the cameras to get their first look at the surface. Current velocity is 145 meters per second at an altitude of about 9.5 kilometers above the surface.
And yes, we're seeing the capsule in front of us, because there was a camera on that heat shield or something.
Nav filter converge. Velocity solution 3.3 meters per second. Altitude 7.4 kilometers.
Now has radar lock on the ground. Current velocity is about 100 meters per second. 6.6 kilometers above the surface of Mars. Perseverance is continuing to descend on the parachute. We are coming up on the initialization of terrain relative navigation and subsequently the priming of the landing engines. Our current velocity is about 90 meters per second at an altitude of 4.2 kilometers.
LVS valid.
We have confirmation that the lander vision system has produced a valid solution and part of terrain relative navigation.
Priming. TBA is nominal.
We have priming of the landing engines.
Back shell set.
Current velocity is 83 meters per second at about 2.6 kilometers from the surface of Mars. We have confirmation that the back shell has separated. We are currently performing the divert maneuver. Current velocity is about 75 meters per second at an altitude of about a kilometer off the surface of Mars.
TRN safety Bravo.
We have completed our terrain relative navigation. Current speed is about 30 meters per second, altitude of about 300 meters off the surface of Mars. We have started our constant velocity accordion, which means we are conducting the sky crane, about to conduct the sky crane maneuver.
This is so cool.
Sky crane
You
maneuver
can
has
see
started.
the sky crane on
About
the
20
upper
meters
part,
off the surface.
here it's the lower part right there. This is just wonderful.
We're getting signals from MRO. Tango Delta.
Touchdown confirmed. Perseverance safely on the surface of Mars, ready to begin seeking the signs of past life.
Okay. Okay. Yeah, next slide. Okay. Perseverance brought along the Ingenuity helicopter. So we're going to have first flight of a helicopter on another planet. So I had to show you the Ingenuity video. Yeah.
Humans just flew a helicopter on Mars, and we've got pictures to prove it. After more than 6 years of development, a long flight to Mars, and some nerve-wracking delays, NASA has finally launched and landed its Ingenuity helicopter.
Altimeter data confirm that Ingenuity has performed its first flight, the first flight of a powered aircraft to another planet.
This is the first powered and controlled flight we've ever completed on another planet, and NASA had to overcome some pretty impossible odds to do it. In fact, there was a chance this flight might not have happened at all. During a final high-speed test of the rotors, the helicopter's systems aborted, and NASA had to beam up a software update from Earth. But Ingenuity finally took to the Martian skies, and thanks to cameras on board the helicopter and on the Perseverance rover, we got an amazing view. A black and white camera on the bottom of the helicopter gave us shots looking down on the Martian surface, while a colour camera gave us a view of the horizon. But it wasn't just the cameras on Ingenuity. Percy the rover was watching the whole thing. There are 2 mast cams on Perseverance that sit about 2 meters or 6 feet off the ground. These cameras recorded both a close-up and wide-angle view of the flight as Ingenuity spun up its rotor blades, lifted into the air, and then slowly landed back down. Ingenuity had to conserve battery power after its flight, so NASA was only able to downlink a couple of black and white images shot by the chopper itself. But the Mastcam Z system recorded the flight in full colour, giving us an awesome view. Ingenuity's flight was billed as a technology demonstration, part of the larger Perseverance rover mission which touched down on Mars on February 18th. The rover is there to find signs of ancient life on the red planet, and it's already achieved a number of firsts, sending back the first full-colour video of a Mars landing and the first audio from the planet's surface. But after Perseverance nailed the landing, it was time for Ingenuity's moment in the spotlight. The helicopter travelled to Mars tucked under the belly of the rover, which is about the size of a compact car. Ingenuity might be a featherweight compared to Papa Percy, but it's also a seriously impressive piece of machinery. It's completely autonomous and self-charging, with 2 pairs of 4-foot-wide rotor blades that counter-rotate to lift off in the Martian atmosphere. The atmosphere on Mars is 1% the density of the atmosphere on Earth, meaning there's not much for the rotor blades to push against to gain lift, and that was a huge challenge for the NASA engineers. That's why the blades had to be so wide. They need to spin at more than 2,500 RPM to actually lift the helicopter off the ground. Ingenuity also needed to be incredibly light. The entire body, including the solar panel, batteries, computers, rotor blades, and landing gear, had to come in at 1,800 grams, or less than 4 pounds. According to the project lead for Ingenuity, Mimi Young, that involved a lot of iterating and shaving off unnecessary mass, ounce by ounce. But even with all those weight concerns, NASA did hide one little Easter egg on Ingenuity, a piece of the Wright brothers' plane Kitty Hawk, which took the first powered, controlled flight on Earth in 1903. Now, more than a century after the first flight on our planet, humans have done the same thing with a 4-pound helicopter flying itself on another planet more than 100 million miles away. To get to this point, Ingenuity had to survive a 7-month journey through space, followed by 7 minutes of terror as its rover descended to the Martian surface. Perseverance had to blast off the helicopter's protective shield and gently place it on the rocky surface of Mars. The helicopter had to survive its first sub-zero night, charge up its batteries by itself using its solar panels, and then spin up its rotor blades for the first time to make sure they actually worked on Mars. And despite a couple of technical difficulties, it passed with flying colours. NASA only had a relatively small window to test fly its drone, 30 sols or Martian days, which is about equivalent to 31 Earth days. They played it pretty safe with this first flight, but now they have the chance to do 4 more flights, going higher and further and potentially even recording sound. And all of these flights are going to bring in more data and more images for the world to see. And that's the real potential of Ingenuity. It's proof that we can bring an aerial dimension to our exploration of new worlds. And who knows, maybe one day we'll be sending little drones to scout around new planets and to venture to places that humans can't reach. Like the Wright brothers and Kitty Hawk, this is just the first liftoff, but it's the start of so much more. But tell me what you think. Do you want to see them torture test this helicopter on Mars? Let me know in the comments below. And while you're here, speaking
and they were able to do more than just the 5 flights that they, okay. Now we're going to talk about Mariner 10, which went to Mercury and Venus. Okay, I want to show you a picture. This is what Mariner 10 looked like. Next slide. Okay, so this is 1973. Mariner 10 was dispatched to Mercury and Venus. They went to Venus first, yeah. Okay, now we're going to show you 2 Mariner 10 videos. They're short.
The launch of Mariner 10. These photographs of the Earth were taken to test the cameras that were to photograph both Venus and Mercury for the first time. After leaving the gravitational field of Earth, Mariner 10 began its long voyage to Mercury. The spacecraft's flight path was carefully chosen to skim past the planet orbiting between Earth and Mercury, cloud-covered Venus. The Mariner 10 cameras at close range were to show us a startling new Venus, a Venus we couldn't see from Earth. The gravitational field of Venus was used to bend the flight path of Mariner 10 inwards towards Mercury. Then the gravity of the Sun pulled Mariner towards its first encounter with the planet. In March of 1974, Mariner 10 flew past Mercury. During the next year, it would perform 2 more flybys. Mercury's orbit around the Sun is 88 Earth days. Mariner 10's orbit was twice as long, or 176 days. These synchronous orbits allowed Mariner 10 to fly past Mercury a second and third time. The path of the first flyby was on the dark side of Mercury. The second encounter sent the spacecraft past the light side of the planet specifically for photography. After another 6-month journey around the Sun, Mariner 10 made its third and final encounter.
Okay, so that's that one. Now we're going to watch the other Mariner one. So Mercury is going to look a lot like our moon, but Mercury doesn't have an area, dark planet. Mercury and Callisto look a lot alike. Okay, so now I want to show you the second video so you can see the actual images of Mercury. You're probably saying to yourself, that looks familiar, that looks like it's not. Lots of green. Soundtrack. So it may have gotten turned down. At one point, I thought this was great. That's one crater on Mercury. Maybe you haven't. I love this. Shadow of Mercury. Gorgeous. Okay, so I've included another one that shows you Venus. Now, the Solar Orbiter in Bepi Colombo was like 2021. This is more recent. So go ahead and show that. So that's that one. Okay, this next one tells about the different rovers we've sent to Mars. Sojourner is the tiny one, it's the first one, and then Spirit and Opportunity were twins, and Curiosity and Perseverance. Okay, Perseverance was obviously built on what we learned from Curiosity. Okay, so next slide. Yeah, we can go on. Okay, Pathfinder is the craft, and it landed with Sojourner rover, 1997. Spirit and Opportunity each landed in 2004. Curiosity landed in 2012. Perseverance landed last year, 2021. This is my third favorite video. Kobe Boykins is a mechanical engineer at the Jet Propulsion Laboratory. And National Geographic put this video together. So let's go ahead and start it.
My fundamental job is to design and build hardware that goes out and explores our universe.
Kobe Boykins is a mechanical engineer at NASA's Jet Propulsion Laboratory in Pasadena, California.
I build things that have gone to the surface of Mars, built things that look back at Earth, things that have gone under the ocean. I've built things that have gone into deep space.
In 1949, the first human-made object was sent into space. Since this time, computers and other tech allow us to see into the universe like never before. Advancements in technology have allowed scientists to consistently reach further into the universe. For example, by late 2018, NASA's deep space probe, Voyager 1, was nearly 13.5 billion miles away from Earth, and yet it's still sharing data with scientists. The United States has successfully landed 8 advanced robots on Mars, and Kobe has contributed to many of these vehicles.
You get to call your family and say, you know, that thing that just went up there in space and is now on its way to Mars, well, yeah, I built that.
1. Main engine start, 0, and liftoff of the Atlas V with Curiosity.
It's an amazing feeling to have hardware that you've touched and you've played with and you got to manipulate in some way on the surface of another planet.
Touchdown confirmed. We're safe on Mars.
So do I have a favorite rover? I mean, it's hard not to love the first child. And so our first child was really the Sojourner rover, which really started our exploration of Mars with robotic vehicles. And so if you don't have that first thing, you know, if it wasn't Kennedy saying that we're going to go to the moon, not because it's easy, because it's hard.
We choose to go to the moon in this decade and do the other thing, not because they are easy, but because they are hard.
It's the same type of thing. We're not going to go do roving exploration on the surface of Mars because it's easy, but we know it's hard.
The scientists and explorers build upon the discoveries and triumphs of those that came before them. But for Kobe, the best part of exploration is not knowing the answer.
You know, there's very few days that I don't actually get some interaction that is new, that I'm learning about, where somebody asks a question where you don't know the answer, and you just have to be open to that experience and sort of go, ooh, I wonder what's going to happen today.
1-0 and liftoff of the Delta rocket with Mars Pathfinder, and the vehicle has cleared the tower.
I was so delighted I found it. Okay, this is my fourth favorite. We've got to see the comet hitting Jupiter. Shoemaker-Levy.
Impacts of comet Shoemaker-Levy 9. Presented by Science at NASA. At the close of the last century, a comet captured into orbit around a planet traveled too close and was shredded by its gravity into multiple pieces, some as large as half a mile or 1 kilometer long. Those fragments would plunge into the planet's atmosphere in a series of impacts. Would the impacts be spectacular, or would the comet fragments disappear without a trace? In July 1994, astronomers around the world watched with bated breath as the fragments of comet Shoemaker-Levy 9 slammed into the planet Jupiter. Dr. Kelly Fast was one of the impact's observers and is now manager of NASA's Near-Earth Object Observations program.
It was just incredible to watch. Such an impact event had never before been witnessed, let alone studied. Ground-based telescopes around the world and spacecraft like NASA's Hubble Space Telescope and even the Galileo orbiter en route to Jupiter were used to observe the impacts. The discovery of the comet by Carolyn and Gene Shoemaker and David Levy gave us about a year to plan our observations.
The impacts proved to be impressive. The fragments, some 21 in all, plunged into Jupiter's atmosphere over the course of 6 days. At impact, they were traveling at a speed of about 37 miles per second, or 60 kilometers per second, heating the atmosphere to at least 53,000 degrees Fahrenheit, or 30,000 degrees Celsius. Like the splash from throwing a rock into a pond, the impacts created giant plumes of material from Jupiter's lower atmosphere, which rose as high as 1,900 miles, or 3,000 kilometers above the cloud tops into the stratosphere. In the aftermath, the plume splashback scarred Jupiter's atmosphere with dark clouds of impact debris, which could be seen for months as they were gradually dispersed by Jupiter's winds. So what were scientists able to learn about Jupiter itself as a result of the impacts? For one thing, those dark clouds of impact debris acted as tracers of the winds in Jupiter's stratosphere, and by following their motion over time, scientists could measure those high-altitude winds. Temporary changes in the aurora on Jupiter showed scientists that Jupiter's magnetosphere was influenced by particles from the impacts.
We are still able to see changes in Jupiter's atmosphere that resulted from the impacts. When the fragments of Shoemaker-Levy 9 slammed into Jupiter, they deposited their own chemical compounds, the impact processes produced some, and others were exhumed from the lower atmosphere. Some molecules, like ammonia, were destroyed by sunlight in the weeks and months after the impacts. But others, like hydrogen cyanide and water, are still seen today. All of that tells scientists about how chemistry works in Jupiter's atmosphere.
Comet Shoemaker-Levy 9 showed us that large impacts still happen in the solar system and were a factor in NASA developing programs to address the impact risk to Earth. From comet science to Jupiter science to the science of impacts, the legacy of that serendipitous discovery by Carolyn and Gene Shoemaker and David Levy continues to this day and into the future. For more impactful stories about comets and asteroids, visit science.nasa.
Okay, so that's that one. Okay. This is my 5th favorite video. We're going to see what all happened to Pluto. Why is it not still a planet?
Most of us grew up with 9. Pluto was the 9th, but it's no longer a planet. I'll explain why not, and also, if Pluto is no longer a planet, just what is it? Pluto was discovered back in 1930 and added to the list of planets. Its orbit is a strange one, taking it for a time closer to the Sun than Neptune, but more of its time is spent beyond Neptune, all by itself. At least we thought it was by itself. In the early 1990s, 2 smaller objects were found in orbits near Pluto's, in what is now called the Kuiper Belt. These discoveries were followed by more objects in the Kuiper Belt, all smaller in dimensions and less massive than Pluto. But even then, some astronomers questioned if Pluto should be considered just another Kuiper Belt object instead of a planet. And this wasn't the first time something like this had happened. In 1801, a new object was discovered orbiting between Mars and Jupiter. It was given the name Ceres. During the early 1800s, Ceres, along with its neighbors Pallas, Juno, and Vesta, were considered planets. But that changed with the discovery after 1845 of many more of what are now called asteroids, also orbiting between Mars and Jupiter. After that, Ceres and the rest were reclassified from planets to asteroids in what is now called the asteroid belt. So it was natural that many would question whether Pluto should still be called a planet, given that many more objects were found around its orbit. Pluto's status as a planet was then put under even more pressure in January 2005 when Eris was discovered in the Kuiper Belt. Eris is practically the same diameter as Pluto, but its mass is around 25% more due to its higher density. The discovery of this more massive object alongside Pluto meant that either Eris should be added to the list of planets, or Pluto should be reclassified to something else. In 2006, the International Astronomical Union, the IAU, convened to decide just what the definition of a planet should be. The final decision was that a planet should meet 3 criteria. 1. A planet is in orbit around the Sun. Check. Pluto orbits the Sun. 2. The planet has sufficient mass for its own gravity to pull it into a nearly round shape. Check. Pluto's gravity has made it nearly round. And 3. The planet has cleared the neighborhood around its orbit. This is done either through collisions or redirecting objects away. And this is where Pluto fails. Pluto accounts for only a small fraction of the mass around its orbit. To put this into perspective, there are thousands of relatively small asteroids, called near-Earth objects, around Earth's orbit. But the Earth's mass is 1.7 million times the rest of the mass in its orbit. On the other hand, you'd need around 14 Plutos to equal the mass of everything else in its orbit. So if Pluto isn't a planet anymore, what is it? At the same meeting of the IAU, a new classification was formalized, called a dwarf planet. What's a dwarf planet? A dwarf planet is one that meets the same first 2 criteria for a planet, but has not cleared the neighborhood around its orbit, just as Pluto hasn't. Plus a 4th criteria. A dwarf planet is not a satellite, like our moon is a satellite of the Earth. Check. Pluto isn't a satellite of any other object, other than the Sun, that is. So Pluto is a dwarf planet, and so are Ceres and Eris. As of now, there are only a handful of dwarf planets, but it's suspected that there may be up to 200 in the Kuiper Belt, and maybe even more than 10,000 when objects outside the belt are considered. This video was made as a collaboration with All Time Numbers. Check out this stunningly awesome video of theirs, The Universe in Numbers, by clicking on this preview.
Yeah, we can stop this now. Okay. Okay, so on the left, that was the best picture we were getting from Hubble. So Voyager did not go to Pluto, but other scientists made sure New Horizons went to Pluto. Next slide. Okay, now we're going to see the New Horizons footage. Yeah, go ahead and start the video. Okay, it starts out really dark. This video has no sound whatever. It does get more light. It just totally starts out dark. But it's very, what I think of as mountainous. But there's similarities with what we saw of Mercury. Yeah. So now we're seeing that some of the rocks look a little bit reddish. Yeah. So red and white. Unfortunately, the video didn't show you the heart, which is a really cool picture of Pluto. But this is the flyby. And what they've done is they stitched together all these individual photos into this montage. And that's what we're watching. It's all stitched up here. So there's parts that look white and parts that look kind of maroon. That looks a little bit yellowish. Looks very mountainous to me, with craters, lots of craters. But it's really cool to be able to see what Pluto looks like. That looks a little bit more like Mercury. Okay, we're close to the end of this, I think. It's cool. Okay, yeah, that's all for that. Yeah, cool. Next slide. Okay, I put this in here so you can get some idea. Mercury is on the left, and then Pluto or Eris are kind of similar size, and Ceres is much smaller. So we can go to the next slide. Okay, now we're on to the Hubble. So next slide. Okay, this is a best of that I just couldn't resist. So we're going to start the Hubble video here. Yeah. Messier, a Frenchman named Messier, named number one. We watched Shoemaker hit the Pillars of Creation. I'm so pleased this was stellar. NGC is the other. Nice. Nice. Yeah, we can go ahead and stop that. Yeah, it's cool. Okay, now we're on to the new telescope, the James Webb. So go ahead and start this video.
A language learning app, for sponsoring this episode. If you're interested, it finally happened. After decades of planning, budgeting, and testing, the most powerful space telescope ever launched on December 25th, 2021. It's a joint mission between NASA, the European Space Agency, and the Canadian Space Agency, called the James Webb Space Telescope. And it has the power to help us understand everything from our solar system to the earliest days of the universe. Just not yet. Webb might have launched in December, but the first images from the telescope aren't expected until at least June. And that's because the launch was only the beginning. Here's what needs to happen before we can start learning the secrets of the cosmos. Ultimately, the reason Webb needs 6 months after launch to become fully operational is because of how complex its mission is. The telescope will observe and analyze everything from planets to stars to the first galaxies. And it's mainly going to do that by collecting infrared light. Unlike visible or ultraviolet light, infrared doesn't really get scattered or absorbed by dust in space. The light waves are wide enough that they can weave right around dust particles, so they can travel much farther. That means collecting infrared light will allow Webb to observe especially faraway objects. The telescope will also be able to study things like old stars and planets that glow more brightly in infrared than in visible light. It'll even be able to pick up light from the very earliest galaxies. So you can see why there was so much hype about this telescope. That said, building a powerful infrared telescope comes with major challenges. For one, Webb needed a giant mirror. Telescope mirrors collect light and ultimately focus it onto a detector. And if you're trying to collect light from some of the faintest, most distant objects out there, you're going to need a lot of mirror. Though Webb isn't the first infrared telescope, it is the biggest. Its primary mirror is about 6.5 meters across, almost twice as wide as the previous record holder, the European Space Agency's Herschel telescope. And while that will allow Webb to make really high-resolution observations, it also meant that the telescope was too big to fit on top of any rocket, even the beefy Ariane 5 provided by the European Space Agency. That's part of why it's taking 6 months to get this thing live. To get it in a rocket, engineers had to design Webb to fold up. Then, after launch, the telescope had to spend a few weeks slowly unfolding, like the world's most expensive origami project. No other telescope has had to do this. But thanks to those years of design and testing, all 50 major deployments worked. Webb unfolded its solar array, which collects sunlight to power the telescope, as well as an antenna, the secondary mirror, and more. In mid-January, it also unfolded the two wings of its mirror. So now, all major parts of the spacecraft are in the right configuration. Along the way, Webb also unfolded its sun shield, which is about the size of a tennis court. It's made of 5 sheets of material coated with aluminum, and it's critical for Webb's mission, because that's the second hard thing about building an infrared telescope. The main source of infrared light is heat, and even something like the moon gives off enough heat that it would drown out the faint signals Webb is looking for. So the telescope has to be incredibly cold. And by blocking infrared light from the sun, the moon, and the Earth, the sun shield is a key part of that. Now, by the time you watch this, Webb should have reached its final orbit, around a point called L2, or the second Lagrange point. If you drew a line from the sun to the Earth, then kept going another 1.5 million kilometers, that's L2. And it's a gravitational fixed point that never moves relative to Earth, so it's always right in line with us. But if engineers parked Webb right at L2, Earth would block a good amount of the sunlight powering the spacecraft, and radio emissions from the sun would interfere with communication. So by orbiting this point instead, Webb avoids those problems, but keeps one of L2's big perks. From Webb's perspective, the Earth and the sun will be in the same part of the sky, so it'll be easier for the telescope to block their heat with its sun shield. But even now, it's still not time to start observations. After its journey, the telescope needs to chill. Literally. Hiding behind its sun shield, it will take roughly a month for most of the telescope to reach its operating temperature, a balmy -233 degrees Celsius. And then the spacecraft will need to be thoroughly tested and calibrated. Engineers will need to make sure the instruments work and that all 18 segments of the mirror are perfectly aligned to within a few nanometers. That way, the individual panels will be able to work together as one giant mirror. Then, at long last, the day will come. The team will give the command, and the James Webb Space Telescope will start collecting data for scientists around the world. And the whole SciShow team will probably be crying tears of joy. But for now, we'll have to wait. Really, it's not a surprise engineers want to get this right. They spent decades and billions of dollars on this project, and it's arguably the most ambitious scientific mission ever launched. And soon, it could get us closer to answering some of the biggest questions we have about the universe. But for now, we'll have to be patient a little longer. Learning a new language is a great goal for 2022, and if that's something on your list, you might be interested in Babbel. But
So now we're going to show you the other James Webb video. Yeah, that one. Yeah. This is the one I just found.
The James Webb Space Telescope, a $10 billion observatory that successfully launched into space on Christmas Day last year. Ever since it launched, the world has been waiting to see its first images that, according to NASA, will deliver us a new view of the cosmos. Although we still have to wait a few months until we start to see these unprecedented views, recently NASA released Webb's first in-focus image of a single bright star, captured as part of a mirror alignment process. But in the background of this image, if you look carefully, you will see something even more interesting. A taster, if you like, of what this extraordinary telescope is capable of. While some of the largest ground-based telescopes on Earth use segmented primary mirrors, Webb is the first telescope in space to use this design. The 21-foot or 6.5-meter gold-covered mirror was far too big to fit inside of a rocket fairing, however, and so it had to be folded up for launch. After Webb successfully made it into space, the 18 hexagonal beryllium mirror segments that make up the primary mirror then unfolded. But for the telescope to work properly, all of these segments have to be aligned with extraordinary precision. The telescope Aligning each segment into one smooth reflecting surface was one of the most important tasks the Webb control team had to tackle since the telescope launched. According to NASA's recent news conference, however, the primary mirror is now fully aligned within a fraction of the width of a human hair and performing even better than expected. Although many other alignment steps and tests need completing before Webb ultimately delivers the new view of the cosmos, this fully focused image is the highest resolution infrared image ever taken from space, providing us with a tiny glimpse of how powerful Webb is. The star at the center is called 2MASS J17554042 plus 6551277, and although it is the brightest thing in the image, emanating streams of light across the universe, it is nothing particularly special. It is just a generic, anonymous star with the right level of brightness used to make sure that the mirror alignment is precise enough, a test star if you like. It's what is surrounding the star that is interesting, the spray of tiny dots scattered across the background, because these specks are distant galaxies billions of light years away that have never been observed before. These mysterious, distant galaxies make this crystal clear image a so-called deep field image, which is an image that has captured the most distant objects in the universe. The Hubble Space Telescope requires days, sometimes weeks, to obtain some of its most famous deep fields, such as this one, whereas Webb will be able to accomplish the same results in just hours. The James Webb Space Telescope is designed to be 100 times more sensitive than Hubble, but the two observatories do not image in the same wavelengths. Hubble is an expert in mainly visible and ultraviolet radiation, while Webb operates in the realms of infrared. It's important to remember, however, that this is only a test image. The glorious vistas, such as those captured by Hubble over the last 30 years or so, will come later, once the observatory is fully operational. But even though it is a test, it does represent the beginning of what we will soon be observing. The James Webb Space Telescope will allow us to peer back in time and capture the first galaxies that formed only a few 100 million years after the Big Bang, potentially transforming our understanding of the cosmos. And I, for one, cannot wait.
Right. Okay. Okay, I just wanted to show you a close-up of our sun. Next slide. Okay, this is my fifth favorite. I love this video. Voyager goes into interstellar space. Let's go ahead and start it.
We have ignition, and we have liftoff of the Titan Centaur, carrying the first of two Voyager spacecraft to extend man's senses farther into the solar system than ever before.
They were launched in 1977. That's a long time ago. We say 41 years, but it's really two generations ago. You can think of what the technology was. Your smartphone has 200,000 times more memory than what the Voyager spacecraft have. And so it's just exciting that we've been able to get it into interstellar space.
We launched two Voyager spacecraft. They were basically the same, but they were on different paths. Voyager 2 was the one that was chosen to do the grand tour. That is to fly by Jupiter, and then Saturn, and then Uranus, and then Neptune. And then after 1989, we began what is now called the Voyager Interstellar Mission. We were on a path we hoped to get to reach interstellar space while we still had power on the spacecraft to transmit the data back. And that's what Voyager 1 did in 2012, and that's now what Voyager 2 is starting to do in 2018. The sun creates this huge bubble of plasma, ionized material. It blows outward at 1 million miles per hour and creates a bubble. And inside the bubble, most of the material has come from our sun, and the magnetic field has come from our sun. Outside the bubble, most of the material comes from other stars that exploded 5, 10, 15 million years ago. We have an instrument which measures the wind coming from the sun, and we saw that in fact there was no longer any measurable solar wind. We had left the bubble, basically.
The team has been looking forward for this for a long time and really working hard in an engineering sense to make this day happen and to keep the spacecraft with all the instruments on so they could, all 5 instruments could sense the heliopause crossing and have data for that. What that means is that the Voyager 2 spacecraft is now traveling in interstellar space.
Well, this just contributes to the number of discoveries that Voyager's been making, and this is one we'd hoped we would have the chance to do, and fortunately, the spacecraft were still operating when they reached interstellar space. It's really quite remarkable. Voyager changed our view of the solar system, really. I mean, we saw these active volcanic activity on Io, we saw the possibility of ocean on Europa. Just time after time, we were discovering things that we had not really even imagined some years before the Voyager mission. What makes it so exciting is that not only do we confirm what we thought we knew, but even better, it tells us where we didn't know that there was something to be discovered.
Okay. And I threw this in. This is about the exoplanets. There might be 5,000 worlds out there. As Carl Sagan would say, there could be billions more. So thank you so much for anyone who hung with us. I'm sorry I may have gone over the 1 hour expectation, but I had a great time putting this together, and I just hope that y'all enjoyed it as much as I do.